And we go directly to our next talk with the title Beyond Autoscaling Application-Aware Optimal Elasticity.
Okay, I'm going to present joint work with Professor Zavataro and Professor Mauro that has been accepted at phase 2019 conferences. Um, I divide my presentation in 3 parts. First one to give you the motivation about our work. Second part with some technical details. And the last part with a case study, a model that we created to show the applicability of our approach and our algorithm. The current state-of-the-art deployment technology as container-based solution like Kubernetes are based on an autoscaling approach. So an approach where each component of an architecture is monitored independently from the others, and when the monitored metrics reach the specified value, the corresponding scaling policy is applied to increase or decrease the number of instances of that component independently from the rest of the system. This is a basic example of code for Kubernetes. In a similar way, the autoscaling services offered by Amazon Web Service allows a similar behavior. We can control each component of our architecture independently from the others. Our approach, the approach that we propose, is different. We won't try to reason at the global architecture level, trying to exploit information about the architecture, about the dependencies in our system, to prepare some plan, some scaling or deployment plan that contain information scaling operation on more than one component of our architecture, also all the component of our architecture. The idea is that, for example, if we have a pipeline of microservices, a pipeline of component with some dependencies, and we have a large increment of the inbound request in the entry point, we already know that probably we should scale more than one component of our architecture to be able to manage the amount of requests received. So the idea is to do it in only one step, with only one scaling plan, avoiding to have a lot of single local scaling operation. The advantages of this approach is main 2 advantages. The first one is that we can prepare our system in a faster way, in only one step, to be able to manage the amount of requests received. And the second one is that deploying more instances of more components at the same time, we can prepare an optimal deployment plan that use in the best possible way, in an optimal way, the new resources that we need to deploy these new components. Our theoretical result is also more general, and it also allows the tool that prepared the plan to use also reconfiguration action that can maybe change some already deployment components with other ones that have a compatible interfaces to optimize the resource usage. So the main difference between the approach proposed and the classical autoscaling approach is that we won't try to reason at the global architecture level, exploring information about the interdependency, the dependencies between the components of our system to create plans that contain operation on more than one microservices in our case, or more than one component of our architecture. Instead, to focus on each component of our system independently from the others. We started from a theorem proved in 2014 that tells that the problem of deploying component-based software system in the general case is undecidable. In this work, we proved that the optimal deployment problem for microservice architecture is decidable, is algorithmically traceable, and we proved it providing an algorithm that solved this problem. The difference between the two cases is that the deployment operation for microservices is easier thanks to the independent between the microservices, so the problem becomes decidable. At this point, to implement, to use our algorithm, we need the free set of information. Information about the dependencies between the microservices. So for example, if we have two microservices, microservice A and microservice B, microservice A use a function and operation provided by microservice B, we will tell to the system that the microservice A depends from the microservice B. We need information about resources. We need to know the amount of resources necessary to host, to run an instance of our microservice, of each component of our system. We need information about the computation node, so machine or virtual machine that host our system. We want to know the amount of resources that they offers to the components and the cost necessary to use one node of the type. So for example, we can tell that the microservice A require 2 virtual core and 1 gigabyte of memory, or that a particular type of machine offer 10 virtual core, 10 gigabyte of memory, and cost 10 euros per day or something like that. The last information that we have to specify is a declarative description of our deployment goal, about the plan that we want prepare to be used during the execution of our system. So for example, we can specify that we want 1 instance of microservice A, 2 instances of microservice B, and we don't want that the microservice C will be deployed or something like that. In the last part of the presentation, I show some example on how we coded this information in our project. The optimal deployment problem is defined as a problem that taking input an initial configuration, a set of available nodes, and a description of the target configuration that we want to reach, and return a set of reconfiguration action that apply to the initial configuration, bring us to a final configuration that satisfy all the user requirements and that is optimal. Optimal means that each computation node used has always enough resources to host, to execute the microservices, the component assigned to it, and the total cost, so the sum of the cost of each used node are is minimal. The algorithm is developed using constraint programming and is organized in 3 phases. The first one, generate and solve a set of constraints that define which microservice must be deployed, how many instances of each microservice must be deployed, and where they must be hosted. The second phase, generate and solve a set of constraints that define which connection must be established between the deployed components. And the last phase, use the information obtained from the previous phases to synthesize the corresponding plan, to obtain the operation necessary to implement the corresponding plan. This algorithm, in the worst case, has an XP time complexity, but in practice, the problem become an MP optimization problem that can be solved using the state-of-the-art constraint solver. To show the applicability of our approach, of our idea and our algorithm, we create a model of a real microservices architecture inspired by an email processing pipeline showed on the iron.io website. And yes, it's a very simple architecture with some parallel sub-pipeline that analyze different parts of an email. To create the model, we used the abstract behavioral specification language that is an high-level object-oriented language that support deployment modeling. In only a few words, it offers some high-level utility to define and create deployment components and to instantiate objects inside them. And to apply our approach, we use an extension of ABS called the Smart Depl that allows us to specify using annotation the information that I described above. In particular, there are three main types of annotation. The first one is used to define computational nodes, specifying the name, the cost, and the amount of resource offered. The second one is usually connected with an ABS class that is used to model the corresponding component and allows us to specify the amount of resource necessary to host to execute an instance of that component and its dependencies. The last type of annotation allows us to specify in a declarative way the deployment rules, the description of the target configuration that we want to reach. All this annotation will be parsed to create an input for an external solver called Zephyrus, that is a configuration optimizer that creates the optimal configuration that will be translated in ABS classes. So after the execution of the tool, we will obtain an ABS class for each deployment plan that we specify that offer two main methods, a method deploy and a method undeploy to execute or undo the corresponding plan. So some example about the annotation to show that they are very easy and understandable. This example is used to define a new computation node. We can specify the name, the cost, and the amount of resource that it offers to host component or microservices in our case. In our code, in our model, we define three different types of computation node inspired by three different virtual machines offered by Amazon Web Services. The second example is an annotation associated with an ABS class called message receiver that models the corresponding microservices. And this annotation allows us to specify the amount of resource necessary to host, to execute an instance of the message receiver microservice, and the dependencies. So with this, with the second part of the annotation, we tell to the tool that to deploy an instance of a message receiver, we need a reference to the load balancer of message parser. This is another example of annotation connected with microservices, with the class, the ABS class that model a microservice, and is similar with the previous one, but instead the dependencies, it allows to specify two methods that in this case allows to connect or disconnect backend instance of the corresponding type with the load balancer. So these two methods will be used in the generated class to connect or disconnect new instance that will be deployed with the corresponding load balancer. The last example is an annotation that it's used to define a deployment plan. There are different fields. The first one is the name of the plan, and it will become the name of the ABS class that will implement this plan. In the second field, we can specify in a declarative way the configuration that we want to reach. In this case, is an initial configuration with one instance for each microservices, and the tool clearly will also deploy all the necessary dependencies that we specify with the previous annotation. The third field allows us to define how many nodes of each type we can use. In this case, 30 nodes for each type. And the last field is used to specify using a logical expression preferences about connection or connection that we want established between the deployment components. The first values local means that If it's possible, we would like that the tool will connect component that is deployed on the same on the same computational node, so local connection. The second one is used to to communicate to the tool that we want that each instance of message parser will be connected with the corresponding load balancer. In our code, we calculate 4 different plans. An initial one with 1 instance for each microservices, and 3 scaling plan for small, medium, or large increments of the inbound request. The biggest plan is the last one that allows to deploy more than 30 instances in an optimal way. So, to conclude with this work, we proved that the optimal deployment problem for microservice architecture is decidable and fully automatable, is algorithmically treatable, and we provide an algorithm that solves this problem. We also propose a different approach respect to the current autoscaling very used approach to deploy and scale system, and we show the applicability of these ideas on a model of a real microservice architecture. As future work, we want to try to speed up our system, our algorithm, that now for the biggest plan, as the last one of the previous slide, require between 20 and 30 minutes. And we want to try to reach a solution that require a few minutes, more or less the time necessary to acquire a virtual machine from a cloud provider, to give the possibility to the user to define and prepare and calculate their plan online when they need them. Thank you.
Yeah, thank you. All right.
For your example problem, first of all, very interesting talk, thank you. Yeah, have you compared your results with a traditional approach of instance local scaling?
Not yet, but this is the goal of my master thesis. So I want to do this simulation between this approach and autoscaling to see what is the difference, if there is other advantages or maybe also disadvantages. And I think to do it for July.
Yeah, thank you.
Thank you for the presentation. It's been a great example. Back for the when you define the specification, right? This is a specification for the optimizer, or I mean, I lost in which specification is this? Is this for the Zephyrus tool?
Yes.
Okay, so
this specification will be parsed, creating the input for Zephyrus.
Ah, okay. So this is the total. So you showed the total specification of the tool, and then this is parsed in the different steps.
So you create the model.
Okay.
You put this specification, all this specification. We call the tool, and all this specification will be parsed, creating the input for Zephyrus. Zephyrus calculate the optimal configuration, and the optimal configuration is translated on ABS classes, other ABS classes that implement the corresponding plan. So after the execution of the tool, you will obtain some classes, and with the deploy and deploy method, we execute it.
The question was, is one specification file, for instance, is one in configuration, and then is parsed and splitted for the different part of the tool. That was the question. I mean,
okay. No, in only one file you can specify more than one plan, and obtain more than one classes. Yeah.
Thank you. Do we have more questions?
Thanks. I have 2 questions. In my experience, it's very easy to scale up, but the real problem on cost is scale down. If you scale down, you must replace components, and it's very complicated to save money, to scale down. Scale up is very easy. And the other questions what I have is, what is your experience? Is these strategies with this centralized component really a good decision? If we want to use microservices, we have autonomy of teams that can do the job for every service. Is the right place to centralize these scaling things in one place in the world of splitting services down to teams?
Okay. So about the first question, the tool offered the method to scale up and scale down the system, because you can deploy and undeploy the plan that you prepare. So for example, in this example, we deploy the system with initial 1. We can execute the first scale, and when it's not necessary, you call the undeploy methods, and this new instance will be removed. About the second question, yes, the thing is that if you have an auto-scaling independent approach, you cannot reach the optimality of the deployment of the resource usage.
That's not my experience. Every service that I see has a very special scaling up and down experience. If you scale down services, you need a very special strategy for every service. And this depends on the content of the service. If you have very easy microservices to translate data, it's easy, but with databases and so scale up and down, it's very complicated. You need a complete process. In the Kubernetes world, we now are going to these operator pattern things that we are integrate for every service a special component to scale up and down and maintenance in these components. And I cannot think about that we can have a centralized place for all these strategies.
Yeah, I think that no, I think that you can adopt, you can create a plan and specify different operation for each component. Also, the annotation, this is the basic example, give you more possibility. For example, you can choose to deploy components on different node of different country. For example, if you use cloud, clearly depends maybe on probably on the application. Yeah, I think.
But the real problem, I think, what you're oversee is the complete life cycle of a component. It exists different problems in the scaling up and down. It is you detect the case to scale up if you have more requests or CPU memory consumptions. But in another place is change the software is another complicated examples to scale up and down components. And how you are formalize in your language these different cases for every component.
Okay, you can specify in this point scenarios. You can specify more scenarios for the same component, changing the cost or the dependencies. And when you create the deployment plan, you can tell that you want some instance with this scenario, some distance with other scenario, and you can customize these aspects using this field. Yeah, you can create different scenario for each component and changing the parameters.
Okay, please, thanks again, our speaker.
Thank you.